Welcome again, Vitas, to a new lesson of this course. Today we'll see how we can write the cross product between two vectors thanks to the Levi-Civita symbol. And I've written again its definition here so that we can recall ourselves what are the components in terms of the indices. So if you don't know what's the Levi-Civita symbol or you don't know what's an even and odd permutation, you can check the video that we have in this course and I'll put the link in the description. So let's start by writing that the C vector is the cross product between these two vectors, A and B. And well, we have to recall that we are going to use, instead of the X, Y, Z components, the first, the second, and the third one. So we are going to see that in index notation, this takes this form, that the ith component of the C vector is this expression. So we'll see why this is true, but first of all you have to remember that this is really a double sum between these two indexes, the J and the K index, because they are repeated indices. So by the Einstein summation convention, you have that this is really a double sum. So it's important to notice these things, and you have to check that there is a double sum, okay? So now that we have taken that in mind, we are going to see what are the components of C. So we are just going to calculate directly this formula. So we are going to arrange the components of the vector in a column matrix, and we are going to use a trick that we can calculate the cross product just by the determinant. So I'm going to do all the steps so that you see that there is no trick, okay, that everything is consistent. And let's see, we can decompose the determinant in this sum. Okay, and now we can put the X component in the first slot, the Y component in the second slot, and the Z component in the third slot, and we form our column vector. So this factor is just going to be A2 times B3 minus A3 times B2. The second one is going to be A3 times B1 minus A1 times B3. And for the Z component, well, the third component is going to be A1 times B2 minus A1 times B1. So you probably know this already, but we're going to check that this formula is true. And we can see already a glimpse of the truth of why this works. And let's see that let's say that we are going to calculate the first component. So I is going to be equal 1. Thus, here is going to be a 1. So if we recall this rule, the Levi-Civita symbol is going to be 0 if there is any index that repeats. So in the sum, every term of this sum has three terms, but we are going to discard all of them which have any repeated index in the Levi-Civita symbol. So we are not going to take into account terms which contain epsilon of 1, 2, 1, for example, or 1, 1, 2. So if we have set I equal to 1 because we want to see what's the first component, J and K are not going to be 1 because that term vanishes. So either J is going to be 2 and K is going to be 3, or vice versa, J is going to be 3 and K is going to be 2, but they are not going to be 1. So we are only going to find in A and B, we have the index J and K, the second and the third components. And you can see that in the first component we only have the second and the third components of this vector. So we are already going to see that this is like a pretty good guess of a formula. So let's see, the first component of C is just epsilon of 1 jk, aj, and bk. You have to recall that I said that j and k are dummy indices because they are summing, but here, if you recall our definition of the free index, I is a free index, because although this is one equation, it's really three, because you can choose, okay, if I choose I equal 1, I have one equation. For I equal 2, I have another equation. A free index is an index that you can choose and you get new equations. So in this case, I is a free index and we have to run I from 1 to 3. So in this case, I need to write it explicitly. In the case of I equal 1, we're going to see the first component of the vector C. And now we're going to do the sum. So here, as I said, we are going to have all the terms that span in j and k, but we are going to discard all the terms that have repeated indices. So j and k are not going to be 1. So we have, for example, where I'm going to write this explicitly, okay? We have 1, 2, 3. Well, let's say that j equals 2. So we are going, now we have taken two numbers, 1 and 2. So k cannot be 1 nor 2, it's going to be 3. J was 2 and k is 3. Now, is there any other possibility? Okay, so we previously chose that j was going to be 2. We can choose that j is going to be 3. And now that we have chosen the numbers 1 and 3, k is going to be 2. Okay, be careful. This doesn't mean that we don't have terms such as epsilon 1, 2, 2, a2, b2. But remember, these terms, and there are a lot of terms, okay? But the only two terms that have indices in the epsilon, well, in the Levi-Civita symbol that don't repeat themselves are only these two terms. The other terms have indices where we have repeated numbers. And remember, because we have repeated indices, this component is going to be 0. So this is 0 and this is 0. And every other term that you can think is going to be 0. So that's the reason we are only going to take into account these two terms, because there are no other possibilities for any other term which doesn't vanishes. Okay, so now we have that this is going to be equal to 1 because 1, 2, 3 is an even permutation. And 1, 3, 2 is an odd permutation. Again, if you don't know what's an even or odd permutation, you can check the video that is going to be in the description. So we have found, by substituting in the components, that the first component of C is equal to this. And you can see that this is in fact the first component. So let's do now I equal 2. Okay, so we are going to do the very same thing. Now, for the epsilon tensor, we are going to calculate the terms of the sum, because remember, this is a double sum, and j and k are not going to be 2, because otherwise, well, they can be, but those terms vanish, so we are not interested in those terms. We are interested in the terms that don't vanish. So we can choose j to be 1. Okay, I'm going to make a table. This time I equals 2, and we can follow two paths, j equal 1 and then k equals 3, or j equals 3 and k equals 1. So we have these two possibilities. And by knowing the even and odd permutations, we see that this first one is an odd permutation, so it's going to be minus a1 b3, and this is an even permutation, so this is going to be plus 1 a3 b1, and you can check that this is in fact the same component as this one. We have minus a1 b3 minus a1 b3 plus a3 b1 plus a3 b1, and now we are going to do the last one. Again, we are going to do our little table. So we only are interested in terms that don't vanish. So we are not going to repeat indices. We have chosen 3, then we can choose 1, then there's only left the 2, and vice versa. We can choose a 2, and then we have only left the number 1. So we have 2 possibilities again. We have 1, 2, and now we have 2, 1. Now 3, 1, 2 is an even permutation, so this is going to be plus A1, B2, and now 3, 2, 1 is an odd permutation, so this is going to be minus A2, B1. And again, this is the same component as this one. So we have successfully proven that this is in fact a good representation in index notation for the cross product between these two vectors. So in order to finish this video, I just wanted to say that there is a property for the Levi-Civita symbol, which is this one. If you interchange two indices, there's going to be a swap of sign. So for example, if we interchange the j index with the I index, this is equal. This is equal exactly, but with this minus sign, because let's say, okay, we have 3 possibilities. Let's say that this order of indices are an even permutation. If we make one swap of numbers, or one swap of indices, we are going to move from an even permutation to an odd permutation. Thus, there is going to appear one minus. We can place ourselves in the other scenario where this is, instead of an even permutation, an odd permutation. So if it's an odd permutation and we swap 2 indices, then we are going to jump from an odd permutation to an even permutation. So if this is odd, if this is an odd permutation, this is going to be an even one, and vice versa. And this also works, for example, if we interchange the k index with the I index. And it also happens when we interchange the j index with the k index. So the fact that this happens for any indices, because I mean, you could imagine that, I don't know, for example, maybe we interchange the j and k index and it stays the same, or nothing happens. Of course, in this symbol, in the Levi-Civita symbol, it isn't the case, but you might imagine that we have another strange object. I don't know, let's say we have an object which is alpha, ijk, and when we interchange I and j, we swap signs, but if we interchange j with k, we don't swap signs. So it only works for interchanging y and j. So this is not the case. When we interchange any pair of indices, whatever indices we want, is going to swap the sign. So this is a property that is called that the Levi-Civita symbol is completely antisymmetric. And this is a very important property because we'll see in the next lesson of the usefulness of the Kronecker delta and the Levi-Civita symbol, well, the usefulness of the index notation. We'll see that this is an important thing to take into account in order to see that some vectors may be involved in a cross product, but we don't really see them. So it's important to recall this property, and we'll use all the tools that we have developed in these last lessons to derive some of the vector identities of vector calculus. So if you have any doubt, please write in the comments. I'll gladly answer to you, and hope you are enjoying this course. See you in the next lesson.